There's partial fraction decomposition. The other ones aren't too terrible, is what I would say. Oh, 1 second. I need to, I guess I'm not sharing my screen right now. 1 second. Yeah, so you don't have like any assignments due this week. You only have to focus on doing the exam on Friday, right? Oh, there are the group works. The group works are due tomorrow if you haven't turned them in already. I forgot about that. I'll send out an announcement so people don't forget. But most people have been turning them in, so. Okay, now we can see everything's good. Okay, so today we're talking about trig sub. And so this is like another example as to why we don't like integration compared to differentiation. Like we want to be using this trigonometric substitution pretty much whenever we have integrals containing the following functions. So if you have a square root of some constant squared minus x squared, you have the square root of x squared plus a squared, or the square root of x squared minus a squared, where a is some constant. This is generally when you want to be using trig substitution. And so the idea is with trig substitution is you're going to want to replace x with either sine, tangent, or secant. And the reason why you end up replacing x with sine, tangent, or secant is because if you do so, you can use the Pythagorean identity and cancel out with the square root in order to get an integral that's easier to work with. Okay. And so how you should be thinking about this, maybe this will be a little bit unintuitive initially, is this, or at least what's inside of this integral, is kind of similar to if we had something of the form of like a squared minus, or maybe I should say like, before I go into that actually, maybe like 1 minus sine squared of x, right? The a is a constant term, which is like your 1, and then your x squared is kind of like sine squared of x. This second term here, oh, and then this is equal to like cosine squared. This term here, it's kind of like having tangent squared of x plus 1, which is equal to secant squared of x. And then this term here is kind of like having secant squared of x minus 1, which is equal to tangent squared of x. Okay, it might not be intuitive now. Maybe it'll never be intuitive, but this is kind of the idea as to what's going on. If you write things out, make these substitutions, like x is equal to sine squared, you can kind of think of this as being like 1 minus sine squared of x, which is then cosine squared. And then the square here cancels out with the square root. So that's the basic idea of what's going on. I'll talk a little bit more specifically now. So first we'll focus on substitution using sine theta. And so if we look at this first case where we have the square root of a squared minus x squared, and we let x be equal to a times sine theta, and then we're making some further assumptions. We're going to assume that a is greater than 0, and we're also going to assume that theta is between minus pi over 2 and pi over 2. We can use the fact that sine squared of x, or sine theta squared of x, or sine squared theta plus cosine squared theta is equal to 1 to obtain the following. So if we make this substitution, x is equal to a sine theta, then we have that the square root of a squared minus x squared is the same thing as having a squared minus a squared times sine squared theta. You can then factor out the a squared and then make the substitution. 1 minus sine squared theta is just the same as cosine squared. So then you get the following square root. Again, we have like squares underneath the square root. Those terms cancel out. So you get the absolute value of a cosine theta. But then we assumed also that a was greater than 0 and theta was between these two angles, which means both of these terms are positive, which means you can then write this as being equal to a cosine theta, which is something you know how to integrate, right? This would just be a sine theta if you took the integral. And so we'll look at the other examples later on, but this is the basic idea. So it's important to understand this equation to understand like, why are we making this substitution? Like, why does this end up working? But of course, it's not really enough to just know this. You have to go through a bunch of examples and develop an intuition, and eventually this will be easy if you do it enough times. Okay, so we'll evaluate this following integral. We should actually already know what this integral is based off of one of the identities we learned earlier. We should find that this is going to end up being inverse sine. Like if you take the derivative of the inverse sine function, you get 1 over the square root of 1 minus x squared. But let's actually show it by making use of this trig substitution. And so we have something of the form, well, we have like a square root of 1 minus x squared that shows up within the integral. So this means that we want to be using the substitution x is equal to a times sine theta. So we just need to determine what our a is going to be. In this case, our a squared is 1. So we have a squared is equal to 1, which then implies that our a is just equal to 1, right? If you take the square root, then this is just going to be equal to 1. And so we're going to let x just be equal to sine theta. And so the goal here, before continuing, is we want to transform everything that involves an x in terms of theta. And so we've already been successful here in the denominator. You just change x in the sine theta, so you'll have a 1 minus sine squared theta in the denominator. But we also have this dx term as well. So you have to take the derivative of x to determine what dx is going to be. And so dx is just going to be cosine theta d theta. And so now we can transform this integral into an integral in terms of theta. And so this is going to be equal to the following. So this is going to be the integral of 1 over the square root of 1 minus x squared. So we let x squared be equal to sine theta. So it's going to be 1 minus sine squared theta. And then we had that dx was equal to cosine theta d theta. Okay, and so the reason why we make this substitution is 1 minus sine squared theta is equal to cosine squared theta by this Pythagorean identity that was written here, just solving for cosine squared. And so this is really going to be equal to the integral of cosine theta over the square root of cosine squared theta d theta. And so if you have cosine squared theta and you take the square root, you just get cosine theta. So this is just cosine theta over cosine theta, which is just equal to 1. So you just have the integral of d theta. And so this is equal to theta plus c, where c is just some constant. And so we're not done yet. The original equation was in terms of x. And so we want our final answer to be in terms of x, but it's in terms of theta right now. So if we want to write theta in terms of x, what would we do? Yeah, go ahead. Yeah, you always want to go back to this original equation that we worked with, right? You want to go back to this thing, because this is the equation that relates x and theta with one another. And this example, it's a little bit easier. Usually you have to draw a triangle and you have to determine a bunch of other trig information. But for this one, to determine theta, all you have to do is just apply inverse sine to both sides. So you have inverse sine of x is equal to theta. You then plug this into theta to get the following. So this is inverse sine of x plus c would be the final answer, which is what we expected, right? This was a trig identity we saw earlier in the class. But now we can prove it using this trig substitution. Okay, any questions about this first example? Okay, yeah, so this is what I would say is like an easier example in the sense that A was really easy to find, like you didn't have to do anything fancy or any sort of manipulations, and then you end up just getting like a theta as your integral. But things can get a lot worse than this. This is like another, like we talked about, like in class on Friday, we talked about the reduction formula. Oh, this is the wrong one. Let me see if I can pull it up. It's like pretty common for these kinds of integrals to have to involve these reduction formulas that we talked about in class on Friday. So it's important to have these in your mind. Like if you're doing like a homework problem or a quiz problem. On the exam, I'm probably not going to make you have to do like any reduction formula stuff. But I'm just saying, like, you should keep these in mind when you're doing the trig sub integrals. I think the next example we do actually is going to involve one of these reduction formulas. Okay, let's continue. Okay, so this is just disclaimer, or not a disclaimer, but like a summary of what we just did. So whenever we have an integral involving the square root of a squared minus x squared, you want to let x be equal to a sine theta, which then implies that dx is a cosine theta. And then you end up getting that this square root will just resolve into a cosine theta, which is usually a lot easier to find the integral of. Okay, so this example is a little bit more difficult. So for this one, it wants you to evaluate the following integral. So we have x squared over the square root of 9 minus x squared. And so usually the first thing you want to do here is you want to determine what your a is going to be. So we have something of the form of 9 minus x squared. So we have something of the form of like a squared minus x squared. So in this case, what is our a going to be equal to? Yeah, a is just equal to 3, right? Because we have a constant 9. This is the same thing as, so we have like a squared is equal to 9. We take the square root, we have a is equal to 3. And it's like plus or minus 3, but we always assume it's going to be the positive number. Okay, and so once we know what a is equal to, we can make the correct substitution for x. So we have something of the form of a squared minus x squared. So we want to make, we want to let x be equal to a sine theta. So we're going to let x, this is going to be equal to a sine theta. So this is equal to 3 sine theta. And then our dx is just going to be 3 cosine theta, d theta. And so now we plug in all of the terms involving theta into the original integral that we have. If we do so, we get the following. So, oh, do you have your phone? Yeah, and so we have x squared is equal to 3 sine theta. So you have to actually plug in for x squared here, change that in terms of theta. So this is going to be 9 sine squared theta. And then in the denominator, maybe it'll drive some of you crazy, but I'm always going to write things out in terms of like what the substitution is and then reduce things algebraically, even though they kind of tell you exactly what it reduces to every single time. Yeah, so this will be 9 minus 9 squared theta, plugging in for x here. And then this is going to be multiplied by 3 cosine theta, d theta. So already it's a little bit messier than the previous problem. Okay, and so let's see what ends up happening here. So we have a 9 times 3, so we'll have a 27 we can bring outside of the integral. And you can see, like, you can factor out a 9 from within the square root, and then you can bring out a 3, so this will be over 3. But I kind of do things one step at a time. So we're just gonna leave it like this for now. So we have sine squared theta times cosine theta, d theta. Actually, before I do that, let's do it like this. Okay, so we can factor out a 9. So this is 9 times 1 minus sine squared theta. And then we have a d theta. Okay, and so we have a square root of 9 that we can bring outside, right? The square root of 9 is just equal to 3. So this is really the same thing as doing 27 over 3 times the integral of sine squared theta, cosine theta. And then this is over. So we have a 1 minus sine squared theta. This is the same thing as cosine squared. So this is the square root of cosine squared theta, d theta. And so we have a square root of cosine squared theta, and then we have a cosine theta. So these terms will cancel out with one another. And so this is going to be equal to 9 times the integral of sine squared theta, d theta. And then you can use the reduction formula here. You can also, there are other formulas you can make use of if you want to evaluate this integral. But we already know what the form is going to be like from the reduction formula, right? So the reduction formula tells us this is equal to minus cosine theta sine theta over 2 plus 1/2 times the integral of d theta. The integral of d theta is just equal to theta. So I'm just going to write this as plus theta. And again, I'm using this formula right here. So this is the formula that we used on Friday, right? So n is equal to 2. So the integral of sine squared theta is minus 1/2 of sine times cosine plus 1/2 of, well, if n is equal to 2, then this just becomes 1, right? So I'm just using this formula. Again, you can also use this equation here if you wanted to, but I just rely on the reduction formulas. Okay, so we're not done yet, right? Everything is in terms, actually, before I continue, are there any questions so far about how we got to this point? Okay, so this is most of the work so far, but we're not done yet. And this is where it gets a little bit harder than the previous problem. So we have a cosine theta and a sine theta, and we also have theta as well. We need to translate all these terms in terms of x. And so what we can do is the following. So you always want to go back to this original equation that we have. And this is going to be your framework for being able to reinterpret cosine and theta, because we already know what sine is going to be equal to. So from this equation, just writing it over, we have x is equal to 3 sine theta. And so we have a sine theta we want to translate in terms of x. So what we can do is we can divide both sides by 3 to get that x over 3 is equal to sine theta. So this is what our sine is. We know sine is equal to x over 3. So that's one piece of information that we were able to write back in terms of x. If we want to get theta, I already asked you in the previous example, so I'll tell you this time. Like to get theta, you just apply inverse sine to both sides. If you do this, you get that inverse sine of x over 3 is equal to theta. So we have this term here. This is equal to inverse sine of x over 3. So all that's left is cosine. Does anyone see, like, how can we get cosine? What do we have to do? Any ideas? I wonder if that would work. I had a different idea in mind, but I guess the issue would there be, I think there's like a dx that would show up, but we already have what dx is equal to. And I guess that would give you something in terms of, I don't know, that's an idea worth pursuing, but in the interest of time, I'm gonna do a different idea. Maybe that does work. Maybe that's more clever than what I'm about to do. I'll look into that after class. Or we can see what the answer, I forget what cosine ends up being equal to, so I can't even check. I want to see if it ends up matching the answer we get. Okay, and so like what I was thinking, the derivative might work, but generally how you want to be doing this, because you might get like a secant or like cosecant, so like the derivative would be harder to relate. You kind of just need to go back to basic trig. And so you draw the following triangle. So you have sine theta. This is opposite over hypotenuse. So we have like sine theta is equal to x over 3. So this is saying that the opposite side length of this triangle should be x. And then the hypotenuse is going to be 3. And then this angle is going to be theta. And so by the Pythagorean identity, we should have at this side length b, we should have the following. So we should have that x squared plus b squared is equal to 3 squared. And so if we solve for b, this is the same thing as saying b squared is equal to 9 minus x squared. So if you take the square root of both sides, you end up getting that b is equal to the square root of 9 minus x squared. We're looking at side lengths, so we have to assume it's going to be positive. That's why it's not going to be plus or minus. It's just going to be plus. And so we have b is equal to the square root of 9 minus x squared. And you should note, this always ends up happening. Like this side length that you end up deriving is equal to what you originally had inside of the denominator. And this should make sense in the sense, well, I'll go into it later. But if we have this triangle now, we can determine what cosine theta is going to be, right? Like cosine theta is then just going to be adjacent over hypotenuse, right? And so this implies that cosine theta is going to be equal to the square root of 9 minus x squared over 3. right? Just looking at this triangle and using the definition of cosine. And so now we have all the terms back in terms of x, right? So this minus cosine theta, let's bring out a 1/2 to make this a little bit nicer to look at. So let's bring out a 1/2. Cosine theta is equal to the square root of 9 minus x squared over 3. So this is minus the square root of 9 minus x squared over 3. This is multiplied by sine theta. Sine theta we found to be equal to x over 3. So this is times x over 3. And then this is plus, so we factor out the 1/2, so I'm just going to write the theta. So we found theta is equal to inverse sine of x over 3. And then this is going to be all plus c. So again, this process was a little bit more intensive. Like it required a bit more work going from here to here than the previous problem. And this is usually what ends up happening. Usually you don't just end up getting an integral like that ends up just being theta. Usually you get an integral involving like other trig functions. So you have to draw this triangle in order to relate whatever your original equation is in terms of whatever else they end up giving you later on. Oh, I forgot about it. So it should be 9 over 2. I pulled out this. So we had like 1/2 here. I pulled both of these 1/2s out into here. Is that what you're talking about, or am I missing something else? Okay. Any questions about this example? Yeah, so this is kind of how they all go, is what I'll say. They aren't really pleasant. This is why people don't really like this section all that much. But if you do enough practice, like it isn't really that bad. You kind of get used to it. It's the same thing at the end of the day over and over again for the most part. Like you write things in terms of theta, you simplify, you reduce things, then you end up getting an integral. You find the integral and then translate everything back in terms of x. So it doesn't really change that much from example to example. Okay, so this is examples where we use sine as our trig sub. Next, we'll be looking at what happens when we have tangent. So we're looking at substitution using tangent theta. And so the derivation is really similar to what we did in the first 2 examples. So we want to use tangent theta when we have the integral of involving like the square root of x squared plus a squared. The reason why we want to use tangent theta in this case is outlined in the following derivation. So we're going to see what happens when we plug in x is equal to tangent theta, and we're going to assume that a is greater than 0 and theta is between minus pi over 2 and pi over 2 to make sure we have like a positive square root. And so if we make this substitution and we have the square root of x squared plus a squared, it then becomes a tangent theta squared plus a squared. You factor out the a squared to get tangent squared plus 1. Again, by the Pythagorean identity, tangent squared plus 1 is equal to secant squared theta. This is what we talked about on Friday. But maybe just like, so if you have sine squared of x plus cosine squared of x, this is equal to 1. If you divide everything by cosine squared, you get sine squared theta, or sine squared of x over cosine squared of x plus 1 is equal to 1 over cosine squared of x. So this is tangent squared and this is secant squared. So this is the same thing as having tangent squared of x plus 1 is equal to secant squared of x. We did this on Friday, but just as a reminder, you can go from this original equation you should have memorized, or like you should have seen this like a billion times throughout your math classes. You can then reduce the following, you can then have like the following equation. So you go from tangent squared plus 1 to secant squared. And then they cancel out, like the square root and the squares cancel out, and you just get a secant theta. And so as a reminder, this isn't something we've derived ourselves, but it's an annoying equation, like integral to derive. It takes a lot of work, so I'm just going to say what the equation is. So from the section 7.2 notes, we have that the integral of secant theta ends up being the natural log of secant theta plus tangent theta plus c. So this will show up every now and then. I think it shows up in the next example. Otherwise, I probably wouldn't have wrote it down, I guess. Okay, so let's go through another example. This one's kind of like the first example we did, except instead of doing x is equal to sine theta, we're going to do x is equal to tangent theta. Oh, it's a little bit different because it's not +1, it's +9. But it's kind of similar to the example that we just did, right? So just like the previous example, we have x squared plus the square of some constant. And so you should be thinking, we should be looking at this 9, and you should be thinking like 9 is equal, or maybe you should be writing like a squared is equal to 9. And so this is going to imply, if you take the square root of both sides, that we have a is equal to 3. And so we have an integral of x squared plus 3 squared. So something of the form of x squared plus a squared. So we should be using tangent theta based off of this derivation we had above. We should end up getting something that cancels out with the square root is the logic. And so we're going to let x be equal to 3 times tangent theta. And then we're going to have that dx is equal to 3 times secant squared theta, d theta, just taking the derivative. And so even though we're doing a different substitution, the process is pretty much the exact same. So let's continue down here. So this is really the integral of 1 over the square root. So x squared now, x squared was 3 times tangent theta. So this is going to become 9 times tangent squared theta. And then plus 9. So plus 9 remains the exact same. And then our dx now is going to be 3 times secant squared theta, d theta. And now it's just a matter of reducing things. So we have a 3. I'll keep it like this for now. So you have 3 times the integral of 1 over the integral. So you can factor out a 9 in the denominator within the square root. So this is going to be 9 times tangent squared theta plus 1. And then in the numerator, I'll just write out the secant squared theta, d theta. Okay, so what ends up happening here? So we have a square root of 9 in the denominator. That's really just the same thing as having, like, you can pull this out and make it so we have a 3. So we'll have a 3 over 3, which cancels out and just becomes a 1. So this is really just going to end up being the integral of secant squared theta over the square root of secant squared theta, c theta. And so you can cancel out, like, the square root of secant squared just gives you secant. So you have secant squared over secant, which will just give you secant. So this is really just going to be the integral of secant theta d theta. And so we see from the previous page, I feel bad about not deriving it, but we're just going to use it. Like, the integral of secant theta d theta ends up being the natural log of secant theta plus tangent theta. You can see if you take the derivative of this function, it ends up being secant theta. Right, so this ends up being equal to the natural log, natural log of secant theta plus tangent theta plus c. And so now it's just a matter of translating everything back in terms of x, right? And so you have to do this triangle business again. You always go back to this original equation relating theta and x. And so if we have x is equal to 3 tangent theta, this implies that tangent theta is equal to x over 3. So that gives us this term. We know tangent theta is x over 3. And so then we draw the triangle. Again, so this is our triangle. This is, the angle is always just going to be written as theta. We know tangent theta is equal to x over 3. So this is adjacent over, or opposite over adjacent. So the opposite side length is going to be x. The adjacent side length is going to be 3. And so we want to determine what secant theta is going to be. Secant theta is 1 over cosine. Cosine's adjacent over hypotenuse. So that means secant theta is hypotenuse over adjacent. And so we need to know what the hypotenuse is. So you just use the Pythagorean theorem here. And again, you'll see we get exactly what we have in the denominator now, like the square root of x squared plus 9. So this is square root of x squared plus 3 squared, which is 9. And so this implies that we have secant theta. This is equal to hypotenuse over adjacent, just the inverse or reciprocal of cosine. And so this is equal to the square root of x squared plus 9 over 3. And so now if we translate everything back in terms of x, this is going to be the natural log of x squared, the square root of x squared plus 9 over 3 plus x over 3 plus c. Oh, and there's, okay. On the exam, I'm fine with you leaving your answer like this. But on the homework, what it wants you to do is it wants you to, this is kind of annoying, and I don't like that it does this, but I don't know how to change it. So it wants you to like take out as many constants as possible. And so you have to go a little bit further on the homework for maybe like 2 problems or so. Not next week's homework, but the homework after, like the homework 2 weeks from today. So what you can do to take this a little bit further is this is really the natural log of x squared plus 9 plus x over 3 plus c. And so what you can do using the property of the natural log, so this is a property of the natural log we used earlier, like in the first week of class, but it's kind of, you don't really use it all that often. So if you have like the natural log of a quotient of 2 numbers, this is the same thing as the natural log of u minus the natural log of v. And so this is the situation we have now, right? Where the u is the square root of x squared plus 9 plus x, and then the v is our 3. So we can split up this natural log as the natural log of x squared plus 9, or the square root of it, plus x. And then this will be minus the natural log of 3 plus c. And so all this is a constant, right? So you can set this equal to some constant d. And so you can write out the final answer in the following way. So you can write out the final answer as a natural log, the square root of x squared plus 9 plus x plus some constant d, right? D is just c minus the natural log of 3. And so I think on the homework, it'll say like absorb as much as possible into the constant. And so sometimes you have like a antiderivative of the following form, and it's going to want you to do this like little reduction and absorb this constant into the c. Yeah, I think you can still just say plus c. But I was writing d just to illustrate that like we had an original constant and we added something to it to get a new constant. But you can just say like plus c on the homework. Yeah, if you have difficulty with this, just email me, and I can help you out. Okay, any questions about this example? Okay. So let's keep going. Maybe go through like 1 or 2 more examples for today. Okay, so again, this is just summarizing what we just did. If you have the integral and it involves an x squared plus a squared and a square root, you let x be a tangent theta. So then dx is always going to be a times secant squared theta d theta. And so then the square root of x squared plus a squared always just reduces to a secant theta. All right, that's what we saw here. So you always have like this 9 tangent squared theta plus 9 ended up reducing into, well, it was a 3, but we ended up canceling out with the 3 here. Okay. Yeah, so for this one's a little bit more annoying in the sense that now we have a bunch of stuff in front of the coefficient. Like all the examples we've seen thus far, what was being multiplied by x squared has always just been 1, but now we have this 25. And so we need to rewrite this in a way, so that way we end up getting something of the form of a squared plus x squared. So like we want to do something with this 25. So let's see what happens. Let's just write out like this is equal to the integral of 1 over the square root So if I want to, I guess I'll ask you to get like an intuition. This is similar to something we did in the first week of class. If I want to write something and make this into the square, something of the form of like x squared plus a squared, like what should I do with the 25? What's that?
We will get like b squared plus 2 squared, a squared, then like 5x squared, and then plus 2 squared.
I think like the problem would kind of be similar. Like if you wrote this as like 5 squared, you're still having like the problem really is, I guess we're actually doing something a little bit different from like the first week, because I think like the first week when we were doing like the integrals and like relating them to inverse tangent and inverse sine, that's what we did. But like the issue is we have like this 25 being multiplied by x squared. So even if you wrote it as like 5 squared, it doesn't really get at like the heart of the problem. Does anyone else have any other ideas about what we do with the 25? Did you raise your hand? Or?
Would we factor it out so we have like 25 x squared plus 2 over 25 and 25 all the way out to the front?
Yeah. So what I would recommend is like you want to factor out the 25. So this is the same thing as 25 multiplied by x squared plus 2 over 25. So you can kind of see the a is going to be pretty wonky in this case. Dx. And then from here, you can pull out a 5 from the square root. So this is the same thing as 1 over 5 times the integral of 1 over x squared, or the square root of x squared, plus 2 over 25. And so in this case, what is our a going to be equal to? Does anyone see? Yeah, go ahead. Yeah, so your a is just going to be the square root of this thing, right? So we have a squared. This is equal to 2 over 25, which then implies that a is equal to the square root of 2 over 5. Yeah, so this example is a little bit more difficult to determine where your a is. But once you know what your a is equal to, you can then just go through the process we've done a number of times now. So we have the square root of x squared plus a squared here. So we want to use x is equal to tangent theta. So we're going to, or a times tangent theta. So a in this case is the square root of 2 over 5. So x is equal to the square root of 2 over 5 tangent theta. If you take the derivative, this implies that this is going to be the square root of 2 over 5 times secant squared theta, d theta. Oh, I forgot to write the dx. 1 second. And so now it's just a matter of substituting in all of your terms to make sure that you can write it in terms of theta. And so this is going to be equal. So we don't have that much going on here, actually. This is 1 over 5 times the integral of 1. And so within the square root, we're looking at x squared. So x is equal to the square root of 2 times 5 tangent theta. And so now this is going to be, if you take the square, you're going to get 2 over 25 times tangent squared theta plus 2 over 25. And then this is going to be multiplied by dx, where dx is the square root of 2 over 5 times secant squared theta. Then you have a d theta. Okay, so the next thing we can do is we can simplify algebraically. We can bring out a square root of 2, like we can factor out a 2 over 25 within the square root. So this is the same thing as, so I'm multiplying like 1 times the square root of 2 and then 5 times 5. You could just see though, like if you factored out a 2 over 25 in the square root and then you pulled it outside of the square root, it would be left with the square root of 2 over 25. So like this would end up canceling out with what you factored out here, and you would just be left with a 1 over 5. But I'm just doing one thing, like just doing things one step at a time. So it's like 1 square root 2 over 25 times tangent squared theta plus 1. Oh, and then let's write the secant squared theta in the numerator like this. D theta. Okay, and so you can pull out the square root of 2 over 25. If you do this, you just end up getting, or like you have a square root of 2 over 5 that you can pull out. So that will end up being, or giving you a 1 over 5 times the integral of secant squared theta. And then within, like this tangent squared plus 1 just becomes the square root of secant squared theta. D theta. So where this 1 over 5 came from, I already kind of explained going from like, I think these terms here cancel out with this. But you can also think you have the square root of 2 over 25, and then you're multiplying by 1 over the square root of 2 over 5. So you multiply by the reciprocal. So you really have 5 over 25, which gives you the 5, and then you have square root of 2 over square root of 2, which becomes this 1. Okay, and so this becomes 1 over 5 times the integral of secant theta. I guess both examples, you need to find the integral of secant theta. Okay, so this ends up being equal to the natural log of secant theta plus tangent theta. This is the exact same antiderivative from the previous problem. Okay, and so we already know, well, we have to do a little bit of work to determine what tangent theta is going to be. So we need to determine what tangent theta is going to be, and we need to determine what secant theta is going to be. So we just take this equation from the very beginning. If we have tangent theta times the square root of 2 over 5 is equal to x, this is the same thing as saying that tangent theta is equal to 5x over the square root of 2. So I'm just taking this equation and then solving it for tangent theta to get the following equation. And so this tells us what tangent theta is going to be equal to. We need to determine what secant theta is going to be equal to. So we draw this triangle again. So again, tangent theta is opposite over adjacent. So the opposite side length is going to be 5x. The adjacent side length is going to be the square root of 2. And then by the Pythagorean identity, the theorem, the hypotenuse is going to be 5 squared plus 2 squared. So it's going to be 25x squared plus 2, which is exactly what we had originally within the integral. And so this implies that secant theta, this is going to be hypotenuse. So 25x squared plus 2. And then this is going to be over the square root of 2. Just using the definition of secant as the reciprocal of cosine. Oh, I forgot the 1 over 5. I'm going to do this over and over again. So there's like a 1 over 5 in front of the integral I forgot to write after doing like the natural log here. So you should have a 1 over 5 being multiplied by the natural log. And so this ends up being equal, let's do like a little wall here. Okay. And so this is equal to 1 over 5 times the natural log. Secant theta, this is the square root of 25x squared plus 2 over the square root of 2. And then tangent theta was just equal to 5x over the square root of 2 plus c. And again, what you can do the same trick as we did last time if you wanted to reduce this further, right? You have like this function of x over the square root of 2. So this really is the same thing as just doing, like this is the same thing as the natural log. I'm not going to have enough space, but square root of 25 x squared plus 2 plus 5x plus some constant d. And I forgot the 1 over 5 again. So this is like a 1 over 5 times the natural log of this thing right here. So this is like how the homework will want it. Again, I was just doing the same trick we did last time, right? Split up the natural log into 2 other natural logs because you have a quotient, and then absorbing the natural log within the constant. I didn't have enough space to write it all out, but okay. But on the exam, I would accept either one of these answers. Either one of these answers are fine. And this would be on the second exam. Again, this isn't on the next exam on Friday. Okay, any questions about this example? Okay, so hopefully you're starting to see like, I mean, it is a lot more work than the other examples or problems we've done so far this semester, but it kind of goes through the same process every single time. So we'll stop here. In class on, I guess, next Monday. The rest of the week is for exam review. So next Monday, we'll pick up by looking at substitution using secant theta. It'll be similar to what we've already done. Yeah, question? Not really. I don't think so. I guess it does happen every now and then, but in this class we won't really do it. Like it'll just be sine, tangent, and secant. Yeah, it could, like it definitely does work. Yeah, and there's like eventually we'll be talking about like hyperbolic trig functions, and you can do something similar using hyperbolic trig functions as well. Yep.
Thank you. I think it's integration by parts, but I was having trouble setting.
Oh yeah, this one you could. I don't know if integration by parts would work that well. You can use substitution for this one, but it's a little bit weird. And it's like one of those where you have to, like to determine what x is, you have to solve. Like you'll have like u minus something. Yeah. That's what
I was checking the answer by doing symbol labs, and then they use integration by parts. So I'm like, they got a different answer.
Yeah, integration by parts could work,
But
yeah, I think u substitution is a lot easier. Yeah.
okay. If we've already been graded on the group works because we presented, do we still need to turn them?
No, I mean if you have like if you look on Canvas and you see you have like a 10 on it, then like you're good.
If you've already graded the first one, then I presented the other two. So.
Okay. Yeah, I haven't done the third ones yet, or the third group work yet, but yeah, you should be good.
But I presented, so
Yeah, you should be good. Yeah.
we had the reading assignment.
There wasn't a reading assignment for this.
Okay.
Yeah, there wasn't a good problem.
So from this chapter here.
Oh, yeah. So like one part was we had the square root of 2 over 25. So I brought it outside. And so this is really like the square root of 2 over 25 divided by the square root of 2 over 5.
Okay.
And that gives you like the 1 over 5 if you like multiply things out.
Oh, tangent square theta plus 1 equals secant theta.
Yeah.
Secant square theta.
Okay.
Okay. I just have a question. There's a problem on here that's on the review guide. Do we have to worry about it?
There shouldn't be. I mean, you don't have to use any trig substitution for anything on here. I mean, there might be one where like you take something like this and you end up getting something like inverse sine or inverse tangent. Because they could look similar to what we have here.
Well, this is not going to be on a test.
Yeah, it's not on the exam.
Great. Thanks, man.
Yep.
So I didn't do this quiz on Thursday. That was my bad.
Oh yeah, you can just email me.